Deep, how do you make your face appear before the slides? What is the trick?
I have no idea. It's probably in Teams.
Oh, is it? Oh,
Yeah,
okay. I
yeah,
have
yeah,
never seen that.
yeah, yeah. It's not. I am
You know
not
how
that.
you know how to do that, Anamika?
I don't. I have seen it. I'll try to figure it out. This really looks nice. More
Yeah.
interactive.
It's like giving a talk in a conference with
Yeah, yeah.
Yeah. Yeah.
the poster behind. Yeah, that's nice.
It also lets me do all of that. So I can change my size and all of that.
Nice. All right, so I think we should get started. So I'll go ahead and briefly introduce our speaker for today's seminar. So today with us we have Dr. Deepjyoti Deka. Dr. Deepjyoti Deka is a staff scientist in the theoretical division at Los Alamos National Laboratory, where he was previously a postdoctoral research associate at the Center of Nonlinear Studies. His research interests include data-driven analysis of power grid structure, operations, and security, and stochastic optimization in social and physical networks. At LANL, Dr. Deka serves as PI and co-PI for DOE and internal LDRD projects on machine learning in power systems, stochastic optimization of interdependent networks, and in cyber physical security. Before joining the lab, he received the MS and PhD degrees in electrical and computer engineering from the University of Texas at Austin in 2011 and 2015, respectively. He completed his undergraduate degree in electronics and communications engineering from IIT Guwahati, India, with an Institute Silver Medal as the best outgoing student on the department in 2009. Dr. Deka is a senior member of IEEE and has served as an editor on IEEE transactions on smart grid. Dr. Deka will be talking to us about realistic learning in power grids, a physics-informed machine learning perspective. Back to you, Deep, with the
All right.
presentation.
I can
Uh,
start now. Yeah, go ahead.
yeah, Darlene, have we started recording? Sorry, should have checked.
Yes, go ahead.
Okay,
All
all right.
right.
Thank you.
All right. I hope everyone can hear me clearly. And thanks for the invitation again. I have met several of you in different conferences and meetings, and it's nice to talk to you. And I'm well aware of the kind of length and breadth of research which happens on infrastructure systems at WSU. So I'm Deep. I sit in the theoretical division or the T division at Los Alamos National Lab, and I'll be talking about realistic learning in power grids. And the majority of the work I would talk would be in this broad area of physics-informed machine learning, right? So just a brief thing, and this is meant for the audience who may not know where Los Alamos is. We are in New Mexico, which is right in the middle of the country. It's one of the oldest Department of Energy NNSA lab, and there's a big defense component to the labs working also. It's a pretty big lab, kind of like PNNL. We have around 10,000 staff, and we are in Los Alamos, which is near Santa Fe. And even though it is in the southern part of US, it is up in the mountains. So we are at 7,200 feet. We have a ski hill just 10 minutes away. We actually have snow right now as well. So it's slightly different from what people would expect from a place in the southern part of the country. Uh, at Los Alamos, though I sit in the T division or theory division, I work with a group of researchers, scientists, and postdocs that we informally call as the Advanced Network Science Initiative. So there are people from computer science, theoretical physics, applied mathematics, engineering, and we study problems which are at the intersection of all of this, including in infrastructure networks, now also in quantum computing, and so on. All right, our website is there. I just listed it at LNC GitHub, and you can email me if you want to know more about the kind of projects that you do and positions in summer and postdocs and so forth. Right. Now, getting to the meat of the talk, I'll be talking about mostly, as I mentioned, machine learning and for estimation problems in power grid. So this is, as all of you already know, this is a map of the large transmission grid or the high voltage lines in the United States. But this is not all. More or less at the end node of every single point in this graph, we have what is known as the distribution grid, which is the low voltage or to some extent medium voltage lines. All right. So distribution grid is the final tier in electricity transfer. This comprises of the lines which take electricity from the substation transformer to the end users, which might be some industrial thing or even residential households. And generally, there is voltage degradation from the transmission to distribution side. That is, you have high voltage lines, and in the distribution, you have low to medium voltage lines. Now, in recent years, by recent years means at least in the last decade, we have had a big enhancement in smart devices and household residential solar and storage devices, energy storage devices on the distribution grid, which at least theoretically has the capability of transferring or sending electricity back to the transmission side. So instead of having a one directional flow of electricity from high to low voltage, you have now energy flowing in both directions. And this bidirectional flow of electricity is kind of a concern for operators and planners, because a lot of devices or even algorithms developed in the traditional distribution grid or on the transmission grid were not modeled or designed to account for this bidirectional flow of power, right? Now, as a result of this bidirectional flow of power or this development of renewables and intermittent source of energy, there is an increase in the amount of variability or intermittency in the distribution, in the power grid itself. So you have a lot of smart devices. If you consider solar or wind, these are not something that can be forecasted exactly or accurately. So you need to account for this kind of variability. Moreover, because some of this renewable and intermittent resources are taking over the generation from certain aspects of the traditional bulk generation resources that we have greater inertia or instability in the grid, and we need to now design and develop algorithms and controllers to ensure that the grid is stable, that is, there is no bad event which happens in the grid despite this intermittency. All right. And as a follow-up, to ensure that you can design right controllers and operators, you need real-time observability and control in the grid. Okay. And this real-time observability in the grid has multiple use cases. One is estimation, of course. So you need to identify who's connected to what on the distribution grid, or on the transmission side, you want to identify when there are lines are off or what lines get disconnected. Is it because of a cyber attack? Is it because of some just animal biting into one of those lines? Once you do this kind of estimation, or even estimation of the parameters in the system as well. So every transmission line in both distribution and transmission side also has included resistances and reactance values. And then this go into what is done in electricity markets. That is a network optimization problem to find the least cost generation to satisfy the load. So the estimation of network as well as its parameters is something which goes into that. So an incorrect estimate can lead to erroneous or suboptimal solutions. Finally, there is a big focus both internally at Los Alamos and also at DOE and other universities about understanding the dependency or the codependency between forest fires and the electricity grid. And I'll just briefly mention slightly more about why this is important. So power grids, including high voltage transmission lines, can result in small sparks or failures once in a while. And if these failures and sparks happen at the wrong time, that is when there is high wind or when the conditions of the ambient vegetation is such that there is less humidity, you can result in fires which can then spread. All right. And such power grid related fires have been happening, in fact, slightly more frequently in the last few years. So the first picture is Ruido. So that's actually a place near Albuquerque, New Mexico, where they figured out that the wildfire which led to evacuation of people was caused by power lines. People are more aware of this large-scale, massive California wildfires, which have been the resultant of power grid related failures of lines under the control of PG&E, and there have been lawsuits and counter lawsuits and all that. Similar such wildfires have also happened in the past in Australia and resulted in policy changes about whether to underground lines and so forth. So just as a motivation for the kind of work that we discuss on, that is estimation or detection of changes or failures or faults in the grid, you know that this can have crucial importance to both grid and even outside of grid, just to communities where humans live. So the problem of real-time observability and accurate estimation is important. Now, what are the ways in which you can do it? So traditionally, we do have a lot of meters or measurement devices in the transmission side. In distribution side too, of late, there have been an influx or an expansion of smart devices which can actually compute GPS time-stamped measurements of voltages or the amount of loads consumed by different users in the grid. And this is in the realm of big data. So you have high fidelity measurements, you get a lot of measurement devices, you can locate it at a centralized authority, and then you can do joint estimation of the different things that you're interested in the grid, right? The problem is such kind of high fidelity measurement devices, which will be called as PMUs or pressure measurement devices, or micro PMUs if you're on the distribution side. They are not everywhere, so it is slightly sparse. So any kind of learning algorithm or estimation algorithm that you design has to incorporate that, the fact that the observability is not complete. Now, talking about the kind of algorithms or the work that you do in understanding the measurements coming from both the smart devices and then doing some kind of estimation would be what will fall in the realm of physics from machine learning. Now, this is, at least in the last decade or so, this has become like a buzzword in the area of AI. So what physics from machine learning is trying to do is to take the best of both worlds, that is the physics or power systems knowledge, and then use them as constraints or intuitions in the development of the standard machine learning algorithm. So instead of having a brute force black box machine learning algorithm, which has been picked up from a different domain and applied to power systems, we want to modify, tweak, change it by using more of the physics or the domain expertise that we have. And the hope is that this will lead to better interpretability in the results of a machine learning algorithm. And the second advantage might be that we'll be able to improve the speed of those learning algorithms, as I would discuss in some of the work that I have done. Right. And hence the advantage is you will be able to at least give some proofs, now that is academically and even otherwise useful. And sometimes if you have more of the knowledge of physics incorporated into your learning algorithm, you may be able to overcome issues which can come because some of the data is bad or you have certain parts of the network which is not observed correctly. Right. The kind of problems that I've been working on, at least for the last 5-6 years, would what I would be calling as learning problems in power grids. So among them, one of them is estimating the topology or the impedances in a distribution grid. So by which I mean I want to identify who's connected to what, which load is on what phase, and if possible, can I estimate the statistics of the load of certain node which is not observed, or the parameters of the lines in the distribution grid. Right. And the related problem with estimation is the problem of locating or detecting faults. That is, the estimation problem would be in a normal operation, who is connected to what. And the fault detection problem would be if the network has slightly changed now, and I had a small signature somewhere, can I pinpoint where exactly the fault has occurred? And again, this is, I'm calling it realistic, by which I mean not everything is observed, not every data is good, there is noise and all of that, and we want to make sure that we want to give some kind of guarantees on the performance of our algorithms, despite having these drawbacks. Right. And I sit in the theoretical division, and as such, part of the work is not just to show that it works empirically well, but also give some guarantees. And the theoretical guarantees of a learning algorithm would be something like saying, if I have voltage measurements, I want to study and tell you the structure of a grid. I also want to understand the question of, if I give you voltage measurements, what length of observations do I need to provide you so that the estimate of the structure that you give is provably correct with high confidence bounds. That is, if you tell me that you need a confidence level of 98%, I should be able to tell you what length of measurements I can require for this algorithm to converge. Other questions are things such as how much noise I can tolerate in the system, how many buses should I have voltage measurements from so that this algorithm should converge. All right. And this is the broad outline of where this talk will go to. So I'll start with understanding algorithm designs for the problem of topology and parameter estimation, particularly in distribution grid. And then I'll go towards a different concept of learning graphs, in particular infrastructure networks, which have been known as graphical models, which is a probabilistic description of the kind of fluctuations that you see in power grids. And finally, I'll also talk about some recent work in the last 2-3 years that I've been doing with one of our postdocs here on understanding how to use neural networks efficiently in power grids, in particular, how to incorporate the physics of the power grid into neural networks to improve its performance. Right? So what does physics informed really mean though? So at least in power systems, it means, can you provide more restrictions due to the domain knowledge that you have in the power grid? So for example, in a distribution grid, as we know that most of distribution grids are operated radially or they're in large meshes, by which a mesh where the cycle or the length of cycle is pretty large. So we have such kind of information or restriction about the structure of the grid. So that is one kind of physics information. The second is the flow physics, which is the power flow equations. That is, voltages, injections, currents are not just independent of each other. They are dependent on each other just by following Kirchhoff's laws. All right. Now, this is a nonlinear set of equations linking injections P and Q with the voltage magnitude V, phase angle theta, and the parameter, that is the impedances of the lines. What you would normally do for the derivation of our algorithm design would be to consider this ambient regime where things are more or less fluctuating around their base values. And then in such a setting, if things are more or less operating nominally, we can do a first order expansion or a linearized expansion of the flow physics, that is the power flow equations, and then write this nice linear relationship between voltage phase angle theta and the magnitude V and the injections active and reactive at different buses in the grid. Right. Now note that the structure of the grid is inherently incorporated into this H1 by X inverse or H1 by R inverse, where H1 by R or 1 by X is actually a weighted Laplacian matrix, where M is the incidence matrix. So M includes is a matrix which links the buses with the kind of lines they're connected with, and R is the diagonal matrix of resistances on the line. So the structure is inherently incorporated here, and it comes in the expression of theta and phi as a function of P and Q, which are the independent variables. Okay. Now this is flow physics, right? So you have structure, you have the power flow equations, which is in the static regime. If you look at dynamics, that is, if you look at faster time scales, you would have swing equations or other dynamical system-based representation of the power grid. I would not go into detail of those work. I'll just briefly mention some of the stuff we have done, but a lot of those flow physics operate in both regimes, that is static power flow as well as dynamics of swing equations. Now we link this physics with what is known as statistical learning, right? So statistical learning normally uses two things. One is sufficient statistics. So you have different probabilistic variables or unknown variables in the system. So for one of them might be the wind speed or the amount of solar forecast or load fluctuations. And you have statistics of those quantities. So you know what the mean is. You can estimate what the covariances or correlations of different quantities are. And secondly, what you do, at least for understanding what length of observations you require for learning algorithms to operate, would be what is known as concentration bound. So what concentration bounds are more or less mathematical constructs which let you understand if you take samples of a particular distribution and then compute a sufficient statistic out of it, concentration bounds teach you or tell you how far these empirical estimates are from the true values. So for example, things such as Chernow bound or Hofding bound or simple case of Markov bounds. So for example, you're taking a sample mean and you're looking at how the sum of a set of random variables are away from the sum of the mean of those random variables by some quantity t, and it bounds you in terms of the number of samples you have, right? So here, that probability that this difference is greater than some quantity is a function of n, which is number of samples you have. So you'd merge both of these together to give a physics-informed machine learning algorithm with some guarantees on performance. So that's the broad idea of what kind of stuff I'd be talking about. Okay. So this is what I mean by provable learning algorithm. You have the different restrictions or information from the physics of the system. You'd want to develop at least a consistent learning algorithm, that is a learning algorithm which is giving you the exact value of some quantity that you're trying to predict, at least in the regime where you have infinite samples. Okay. And then you'd look at the regime of finite samples and then use statistical learning and concentration results to say that even if the result may not be exactly correct, can you give it is correct with high probability. That is, on majority of the independent runs that you run of this algorithm, is going to give you the correct answer. Okay. Let me talk about the first kind of work that we discussed in this work, of physics and machine learning. So there is this problem of, let's say, estimating or even verifying the structure of a distribution grid. Let's assume for this part of the talk that I have voltage measurements or PME measurements of the voltage at all the buses in the distribution grid. Okay, so all of these blue circles are the buses in the grid. You have time series of voltages. Okay, now if you have time series of voltages, you can compute the mean and covariance between the voltages at different buses in the grid. Let's say you do not know what the structure of the grid is, so none of those lines are observed. You want to estimate the operational topology, so you want to know who's connected to what. Okay, and the way we were able to solve this problem is that we looked at this quantity, which I'm calling the variance of voltage differences. So what I'm doing is I'm taking the voltage at two nodes A and K, taking the mean out and looking at the second order statistic, right? So that's the voltage difference square expectation. So that's the variance of the voltage differences. Now, what we showed that in a distribution grid, which is radial, this variance of voltage difference has this nice quality, irrespective of the fact that there might be loads which are fluctuating, there might be solar energy which might be fluctuating and so forth, that is variance increases along all possible paths in the distribution grid. So for example, if you take three buses A and B and C, such that the path from A to C in the true grid, which you don't know about, that we're trying to estimate, if the path from A to C goes through bus B, then this variance of voltage difference quantity between VA and VB is less than that computed between VA and VC. And this is true irrespective of the kind in which they're oriented. So it happens when it goes like that, irrespective if A is further down, if C is further down instead of A, and the path from A to C goes to B, or if A and C are both leaf nodes or end nodes in the distribution grid, and B is somewhere in the middle, so that the path from A to C goes to B. And this just follows from analysis of the power flow equations that I briefly mentioned. Okay. Now, if you have this quantity variance of voltage difference statistics that you can compute using your samples, there's a very easy way of estimating the structure of the grid, right? So you, for every single pair of the distribution grid, for every single pair of buses, A and B, you compute this quantity, phi AB, and because it increases along all possible paths, all you do is you construct a spanning tree, that is the minimum weight spanning tree, which can be constructed greedily. So you just keep on adding edges one by one with minimum weight so that you construct a radial tree, and that tree is guaranteed to be the true structure of the grid. Okay. Now, what is good about this algorithm is it does not require any information other than the voltages. So you do not need to know what the value of injections are. You do not need to know exactly what the parameters of different lines are. And we analyzed it further and saw that it is not specific to basically power flows. It would work for any kind of infrastructure network where there is monotonic flow. By monotonic flow, what I mean is that there's potential difference between two buses, and if the potential difference increases, the flow between those two buses increases. So that holds for, let's say, a water network or a district heating network, where instead of power flow equations, you have thermodynamic equations, or even for gas systems. And given it is a simple spanning tree algorithm, and we know that these voltages come from, let's say, a distribution, and you can compute this expectation, we can also look at this consideration results and find out the computation complexity as well as the sample complexity. That is, we can find out what is the length of observations of voltages that you need to observe so as to give a correct answer. So we can give a guarantee of this kind. So for example, if you give me some particular small value eta, if I have V square log V, so where V is the number of buses in the grid, in the distribution grid, if you have order of V square log V number of length of samples of voltages at different nodes, you're able to provably estimate or recover the topology of the grid with probability 1 minus epsilon. Okay. Note that if you need higher and higher confidence, it is, which means lower and lower eta, this order goes as log of 1 by eta. So if you have a higher confidence level or lower error rate, the number of samples that you require would grow. Okay. And then this is a small test case on a 33 bus test system where we use MetPower test samples for voltages, by which I mean it's not linearized voltage measurements, but basically the nonlinear MetPower solvers samples. And this algorithm works fairly well. So if there is no noise or the noise covariance is less than 5%, you can see that even with just 100 samples, you're almost learning the exact topology. Note that this algorithm also does not take any input of what the potential set of lines can be. So in a realistic power grid or a realistic distribution grid, the operator would have at least some knowledge that certain lines just cannot exist by themselves. So in that setting, the number of samples or voltage samples that are required to learn the topology would be even less, because now you can just rule out certain kind of edges or lines to be non-existent. All right. But the drawback of this algorithm is you have or you require voltage measurements at every single bus in the system, right? And that's kind of unrealistic. So moving on, what we did is we tried to see, okay, how will this algorithm work if there are missing nodes or unobserved nodes that are not adjacent? So consider this setting on the left-hand side where the dotted circles correspond to buses where you don't have voltage measurements. Now, if you just ran this spanning tree algorithm, that is, you compute this variance of voltage difference statistic, and you just do the Spanning tree, and this is again theoretically can be shown that you can have wrong connections coming in. So for example, in this particular network that you reconstructed, which is a tree, you have nodes which are in CP and nodes which are in CP2 that are just 2 hops away, right? So they are connected to the same node, but in reality, there are actually 4 hops away. There are like 3 nodes in between them. So the task now happens that if you learn this spanning tree, can you then identify where the missing nodes are and then insert them in the tree to construct a real network. And you actually figured out a way of doing it. So what we now did was, instead of just looking at this phi, which is the variance of voltage differences, we looked at phis at node triplets. So I look at this quantity, which is phi ACI plus phi ACJ minus phi CICJ. So it's computed 3 quantities. So I compute the one between, let's say, A and this. Then I compute the one between A and CP2, and I subtract the quantity between CP1 and CP2. Now, if I look at this node triplet quantity, what we're able to show is that this has this very nice structure in which it kind of clusters. So if you look at this matrix, where I'm grouping nodes which have a same parent or the same neighbor in this set CP, CP1, and CP2, that is this, and that. If you compute this node triplet quantity, if the nodes have the same parent, it has a quantity which is positive. If the nodes have a common grandparent, that is their parents share a common parent, then the value is 0, that's CP1 and CP2. And if they're further away, then this quantity takes a negative value. So what you can effectively do is, for the computer graph like such as this, you can take all the children and A, compute this graph, compute this matrix, and then kind of cluster them and separate out the ones which have a common parent, and then insert a common parent and keep on building the grid. Okay. Now this is again restricted to a radial grid, but then this is what we came up with in a learning algorithm. You construct a spanning tree, you cluster these matrices, then you start off from the leaves of the grid, you find out their parents, you insert them, and you keep on doing it iteratively by finding missing parents, inserting them, and going on. And eventually you are able to learn the full distribution grid, even though you had observability only at a subset of nodes. Now this algorithm would work exactly correctly if the unobserved nodes or the missing nodes are separated by 2 hops, that is, they are not adjacent to each other, right? So that's again another learning algorithm that we developed, and you can, just like in the previous case, you can look at the sample complexity as well as the computational complexity associated with learning this algorithm. Okay? Now, while having some amount of missing nodes in the grid is realistic, what is even more realistic in a distribution grid is where you don't have any measurements at all in the intermediate part of the grid. So you can consider a system where all your measurements are located at the end users or the households in the system. And this smart devices are giving you, let's say, time series nodal voltages and injections, that is samples of loads at the leaves. Nothing internally is observed. So now what we can do is we can think of a problem where you want to understand who's connected to what, that is reconstruct this grid. And not just reconstruct this grid, but also talk about estimating or learning the impedances of all the lines in the grid. Now, this problem is actually coming from a discussion with folks at Southern California, where they did discuss about the fact that they have a lot of smart devices now that they can effectively use in providing grid resources, but they have no idea about what the parameters are or the values are. So these values as well as the topology is something that is a prerequisite for them to run a control algorithm on the distribution grid. So let's talk about how we devise or a learning algorithm to do that. As I mentioned, you have smart devices, the end users. So these are the solid blue circles. Nothing is known on the internal part of the grid. But if you have time-stamped observations of voltages and injections, as before, you can compute statistics of voltages. So you can compute the mean voltage, you can compute the covariance. Similarly, if you have injection samples of the end users, you can also look at the mean and covariance of injections, both on the active side and the reactive side. Not just that, you can take these voltage samples, you can take these injection samples, you can also compute something such as a cross covariance, all right? So the covariance of voltage and injections. So now to develop this algorithm, what we understand is if you have injections and voltages on certain part of the grid, you can possibly compute what is known as the effective impedance or the effective resistance between 2 buses. Now, from a power systems concept, what it means is if you inject 1 unit of power at A, take it out at B, how does the voltage change between A and B? So that is what is known as an effective impedance. So you're effectively converting the entire rest of the network or the grid into a straight line, which is linking between A and B. And this has this formula. It depends again on the structure and kind of connections between A and B. One advantage that you have in effective impedance in a distribution or radial grid is that effective impedances are additive. So the effective impedance between node B and let's say this node plus the effective impedance between this node and A would be this, as sum of both of these would be equal to the effective impedance between B and A. So it's additive along the paths in the radial distribution grid. So now you have the voltages, you have the injections. Let's say you computed the effective impedances between all observed leaves in the distribution grid. And we know that that's an additive metric. So now I can reduce this problem of learning the distribution grid to a standard graph learning algorithm. I need to know a graph. I have computed the distances between all the n nodes or the leaves in the graph. Can I do it? Well, it turns out there's actually a nice algorithm called recursive grouping algorithm developed by Anima Rankumar, who's at Caltech right now, which can learn or construct this graph. So once we have computed this effective impedance, which is where the power flow equations would come into picture, we can then use those equations into a recursive grouping algorithm and reconstruct it. And what this recursive grouping algorithm actually does is it finds out that if you have distances, which in this case would be effective distances or effective impedances, these effective impedances would satisfy certain kind of constraints by which you can identify the leaf nodes or end users which have a common parent, all right? And that is what I'm writing in this first equation. Without going too much into detail. Secondly, once you have identified a common parent, you can use the second equation to not just identify the common parent, but also measure the distance or resistance of the end user with the parent, which is unknown. So now we have these two conditions. So now we can design a nice learning algorithm. So what you do is you have this set of buses that you have voltage injections at. You compute the effective impedances between all pairs of nodes that you observe. You use this first rule to identify the set of those leaf nodes or final nodes that you have that have a common parent. And then you learn the effective impedance of that common parent. Okay, so for example, A and B have a common parent B. You identify that B exists, and you draw edges and give it a effective resistance value. You do it for other nodes as well. In the next iteration of this algorithm, you consider only the nodes whose parent you have not discovered. So this is this blue circle and all of these circles with unknown parent. And then you run the algorithm again. You find out nodes which have a common parent. You draw edges. You have the set of now the set of parents whose parents you don't know, and you then keep on running this algorithm. And finally, you are able to learn the entire structure. Okay. So that's a very nice iterative algorithm that uses only end users, and the benefit is that it's not just learning the topology; it is also learning the values of the impedances or effective impedances of all edges in the grid. Okay. So the task now becomes how do you learn the effective impedance? All right, this quantity, which is dependent on the inverse Laplacian matrix. Well, it turns out if the injections are uncorrelated, by which I mean if the fluctuations in the loads at different nodes are uncorrelated, it's fairly simple. For every pair of nodes, you have to solve a set of linear equations with two variables. It gets slightly more convoluted if you have correlations between injections, but then again, it's a large set of linear equations that you satisfy that you have to solve, but you can still invert this matrix. This matrix is known because you have all the injections. This matrix is known because you have all the information on the voltages and injections, and you invert it to identify what this matrix is. And once you have learned this H inverse matrix, you can take entries in this matrix and learn the effective impedances between all node pairs that you have observed. Okay. And as I mentioned, given these are all statistical quantities, that is, you can look at how many samples you require to estimate the cross covariance of the voltages, the injections, and so on and so forth. And you can show that you can then look at, analyze this concentration result and give a sample complexity result for when this algorithm works, which is what we did. So we see that between uncorrelated to correlated injections, that is, correlations would lead to intuitively more number of samples. You get an order V extra in terms of the length of the observation window that you require to learn the impedances and the structure correctly. Okay, and these are some sample results of running simulations on it. So again, all of this simulations is with the fact that we use nonlinear Met power samples. We do not take any input or information about the fact that there might be some knowledge with the operator that certain edges do not exist or do exist. Okay? And you can see that we run 1,000 samples. The recovery is almost close to 1. And it also doesn't seem to, at least in our simulation, doesn't seem to depend that much on the amount of correlation row that you have between the injections at different nodes. Okay. And what I discussed was for single phase or balance case, that is, you have just one voltage and one injection at a particular node. You can also extend some of this work into the setting of unbalanced multi-phase systems, that is, where you have three-phase or a subset of phases at different buses in the grid. And then you can not just learn the structure, learn the impedances, but you can also learn the phase on which every single bus in the grid sits on. Okay? And this is that work that I mentioned. I would not go into detail in it, but yeah, it can extend to three-phase unbalanced systems. The only setting is, again, from single phase to three phase, the equations become slightly more complicated. The complexity results would be slightly more complicated to analyze. Okay? But in this part of the talk, I only talked about radial grids, right? So distribution grids are radial. But what about if there are mesh networks? So considering a microgrid setting or even large transmission grids where you can have loops in the grid, even though those loops might be large, right? The other setting is one where the voltages and injections and so forth might be correlated with each other. So this part of the work that I discussed dependent on the fact that the injection fluctuations for majority of it are uncorrelated or have low correlations. So look at loopy grids. We move on to a different structure. We look at what I mentioned as graphical models. So these are probabilistic ways of analyzing the structure of distributions of random variables. And we'd use it particularly in the power grid context to understand if they can be used to learn the grid. Okay, so for people who may not be aware, the one slide description of what a probability of a graphical model is, it gives a structure in the distribution. So for example, consider three different random variables. You have temperature, you have load, you have the price of electricity. Okay. Now technically they are all correlated. If you have high temperature, you have higher load, and you pay a greater electricity bill. But what turns out is the flow of information is actually in one particular way, right? So temperature actually impacts load, and load impacts the price. And that particular dependency or the structure in the distribution is called conditional dependence, and is what is incorporated in a graphical model. For the setting that we discuss, all we need to know is look at the inverse covariance matrix to model the structure in the distribution of temperature, load, and price, as well as the dependency in between them. Okay, so in our setting, we have, let's say, voltage measurements, which is voltage phase angles or magnitudes. Now, if you look at the distribution of, or the graphical model of loads and injections at different buses in the grid, and to model it, I look at the inverse covariance matrix of voltages, phase angles, and magnitudes. You can show that a graphical model, in this case, for a power grid of this kind, includes edges between the nearest neighbors, that is, let's say K and I and K and J, as well as edges between two hop neighbors in the distribution grid. So for example, I and J, which are actually two hops away in the power grid, would have a connection or an edge in the graphical model. So now, to estimate the structure of the distribution grid, having estimated, let's say, the graphical model correctly, all we need to do is to remove these spurious edges between two hop neighbors to know what the true underlying grid is. And we have developed two schemes for doing it, one of which I'm calling as edge removal or counting, and the second is I'm calling it thresholding, right? And these are exact, that is, they operate correctly for radial grids, and they also extend to distribution into loopy grids or mesh networks, but with certain restrictions. Okay. So one of the algorithm is edge removal and counting. Again, without going into too much into detail, what we do is we'll use the voltages, find the inverse covariance matrix, learn this graphical model, which is additional edges over the topology edges. So now the way we identify what is a true edge versus a spurious edge is we remove a set of nodes from this graphical model. Let's say I remove J and I, and then look at what happens to the rest of the network. So for example, in the graphical model, there is a path from node L to node K, which goes through either J or I, right? So you can go like this. You can also take that path from L to I and then to K. But if you remove both these edges I and J, you can see that both L and U are disconnected from T and K. Now, this disconnected property is something that we show that it holds only if the edge between the two nodes is a real edge and is not a two-hop edge. So you can identify what are true edges separated from the spurious edges. And there is one more additional step which leads to the discovery of leaf nodes. That is because leaf nodes are not something that will disconnect one part of the network from the other part of the network. But once you have learned the edges between non-leaf or internal nodes in the system, we can identify the leaf nodes by looking at common neighbors. Okay. Now, this algorithm is exact for radial network. We also show that this algorithm is able to recover a loopy graph, that is a graph with cycles, as long as the cycle length is greater than 6. And that is something which is very commonly true in, let's say, microgrids or even meshed distribution grids. That is, you would not have small triangles in the system, you'd have large circles. Okay? There's one more algorithm using the same inverse covariance matrix or the graphical model, and that I'm calling as thresholding. So here what we do is we look at just the magnitude of the entries of this inverse covariance matrix, and we can show that the entries corresponding to, that is the sum of the entries corresponding to this submatrix of phase and submatrix of voltage for spurious edges have a positive value, and for true edges have a negative value. So a simple thresholding operator is sufficient to learn the true edges and separate them from the spurious edges and learn the radial grid. More importantly, and which is pretty nice, is that unlike a cycle length of 6, you just need a cycle length of 3 to ensure that this learning algorithm is able to learn a meshed or loopy network. That is, as long as there are no triangles in the power grid, which is very commonly true, you are able to learn the grid accurately. Okay, and this is using this concept of graphical model sparsity and again the signs of entries in it. Okay, and this is again an algorithm. It's a loopy grid which we constructed. So we took a radial grid, added some new addition lines, and then we show that again the algorithm would converge. That is, if you have higher and higher number of samples, they would converge to the exact estimate or topology. The performance, of course, is going to be better if the amount of noise in the system is less. Okay, and in our paper, we've also studied with some reviewer feedback and given some results on what is the max amount of noise and the max amount of injection correlation. Okay, so because injections are correlated, the graphical model might have additional edges. So we give some results on how much noise and injection correlation this graphical model-based learning algorithm for topology is able to tolerate and still give provably accurate topology of the underlying network. Okay. Again, just briefly going through it. I talked about, again, a graphical model for voltages. I talked about particularly the balance setting where you have just one voltage injection per node. It easily extends again to three-phase unbalanced systems also. Just that the probabilistic model for how the distribution of voltages would look like is way messier, but it again has this nice graphical structure. You can remove edges and do all of those things. I did mention that we can extend it from the static power flow equations. That is on the left hand side. This is where I did all of the analysis till now. So I looked at voltage, magnitude, and phase, which comes from the power flow equations, which are not temporally dependent. An easy extension to a dynamical case is the setting of swing equations or other linear dynamical network where the voltages, magnitudes, or the frequency or phase angle change because of imbalances in the system. The entire architecture of graphical models actually follows through even in this case. The only difference is, well, the graphical model or the structure is given by the inverse covariance or correlation matrix in the static power flow case. In the setting with dynamics, you'd have to look at the inverse power spectral density. So you have to look at the correlations, you have to find the Fourier transform, you have to invert it. But then after that, all of the structure of neighborhood, two-hop neighbors, this thresholding and all of that would actually work. And not just that, because you can analyze static Gaussian random variables or sub-Gaussian random variables and give concentration results, you can also give concentration results for inverse power spectral density and do this kind of computations that you have done in some papers. Okay. Now, I did not mention a lot of research and other efforts which are going on, primarily because I wanted to push this tutorial paper also. So I wrote it with Vasilis Kekatos at Virginia Tech and Guido Cabraro at NREL. So we have covered a bunch of papers or research work that has been done. Some of those, it's an incomplete list of researchers who have mentioned on the left-hand side. And this is in the final stage of review at Transaction Smart Grid. And we have covered the different ways in which you can look at understanding or learning distribution grid topologies. A majority of my work looked at statistical quantities such as means, covariances, and properties. There are also people who have done work on just using standard linear systems with single samples and doing all of this estimation. There are people who have looked at physics guided or information guided from simulators in identifying not just topology, but changes in topology and so forth. So I request you to look at this tutorial paper for more details on work in this area. Okay. Finally, sometimes these models also don't work, right? So all of my algorithms would assume at least you have all information at a leaf nodes. So that's at least 50% observability required in the system for the algorithms to converge exactly. Okay, and I'm assuming linearized power flow models and all that, which are good in the ambient regime, so when things are more or less operating properly. But in a setting when there are large fluctuations, you have a fault, a change might occur, there can be large jumps in voltages. Some of those algorithms might not work. They've been worked by some folks on using nonlinear learning algorithms such as kernel methods by Professor Xenakis at Minnesota. People have also looked at Koopman operators and also used neural networks. As such, we started at Los Alamos with postdoc Venting. We started looking at also understanding use cases where neural networks would work. And one particular use case that we tried to look at is the problem of fault detection or localization. That is, you know that a fault has occurred, let's say. You want to identify where exactly in the network the fault is. And what we've observed is if you use more of the physics or intuition in the design of neural networks, often those neural networks work exceedingly well. Okay? And I'll briefly go through some of the work in this area. So let's discuss the problem of fault localization, okay, under realistic data. So effectively, fault localization in a power grid is a graph localization problem. Let's say voltage is at a few buses in the grid. You want to locate where the fault is. And then you have some historical data or a simulated data from one particular test case of that particular grid that you can use to train your neural network. Now, there are several other methods, which are, I would call them classical methods, on using impedance-based or traveling wave-based methods to identify the fault location, or using statistical machine learning. The problem with this kind of methods is they often have a very high requirement on observability in the system, kind of similar to my work on learning distribution grid topology. So you require 50% or more observability to identify the fault accurately. But in a realistic setting, we might have the smart meters or these high fidelity meters only at a few buses, but you still want to do at least some estimation of where the or localization of the where the fault is. Okay. All right. So let's look at a realistic regime. You have again voltages from few buses. And then this historical data might have few labels, by which I mean you have, let's say, time series of voltages and all that from the grid, you know a fault has occurred, but maybe a lot of those samples do not have a recording of where the exact fault was, which was verified by an operator. And a lot of this data might also have noisy features to it. By noise, I mean not just Gaussian noise added to it, but let's say fluctuations because loads have changed, solar changes, someone opened, regulator's value has changed and all that. Okay. So one way in which you can look at this fault localization problem is to do what is called a black box neural network. So I mean, you pick a neural network, you have a set of features, which may be just voltages or some aggregated features based on these voltages. And then you predict an output, which is the location of the fault, all right? Instead of doing that, what we propose to do is to do what I will call as physics-informed neural network. Okay? And what physics-informed neural network would be using our intuition of physics or intuition of power flows to guide the design of the features, which will go into a neural network. And the second aspect of it is you use the physics also in the training. So by which I mean, if you have fewer labels, you can use the physics of the system to create spurious or augmented labels on certain unlabeled part of the test data set that you have. You can use noisy training or robust training. You can do certification based on physics and also some regularization based on physical laws that you know that your observed voltages or features in the system satisfy. So I'll go briefly into it. I will not talk about regularization, even though we have some work into it. Just to begin with, we have observed, and this is again fairly straightforward, that instead of just taking raw voltages, if you have some knowledge of the underlying base case test network, that is with the impedance Y or even just the structure of the grid, if you do some kind of a spatial averaging, which is what I'm doing, right? I'm looking at the change in voltage delta U, and I'm multiplying it with this Y matrix, which is including the structure of the grid. And you have this kind of, if you use that as an input feature to your neural network, the spatial averaging, which is leading to at least some spread of information in the network despite having very few observations of voltages. Using just this feature into a convolutional neural network leads to massive improvement in actually the performance of your output. And LAR here means the location accuracy rate. So it is a number of test samples where you're able to correctly identify the true fault for different kinds of faults. So this is three-phase, this is line to ground, line to line, double line to ground. And you can say that when you have a lot of measurements, by lot I mean close to 30%, even SVM is a very standard machine learning algorithm, or neural networks are able to predict good answers. But a CNN or a convolutional neural network with this kind of neighborhood-based information incorporated into the features leads to improvement in the location accuracy rate. But that's just the first step. So just by using a simple feature design, you're able to improve the performance. But let's look at what happens when the labels that is associated with the training data, that is where the true location of the fault is in training, is limited. So I consider a case where I'm looking at line to ground faults with 15% observability. Our standard machine learning algorithm, but with the right set of neighborhood-based features, is able to give a correct answer on, let's say, 92% of test cases. But if I reduce the label rate, that is, I remove the labels from, let's say, 75% of the training data, you can see that the performance of the learning algorithm actually goes down drastically. It goes down to close to 50%, which is almost like a coin toss now. Okay, and this is nothing non-intuitive, right? It's very standard. If you have removed the labels, you cannot use that particular training data in your training. So you have fewer samples to train on, and hence the performance goes down. So what we did to overcome this problem is we tried to do fault localization by looking at a two-stage process. Okay? The first stage is what I talked just before, which is using a graph that embeds the structure of a network using neighborhood-based embedding into it. Get outputs, use a neural network, and learn it using standard cross-entropy and regulation-based training. What you observe is that even if your samples are low or the labels are low, you still approximately get the location correctly. So here what I'm showing is the top 5 lines where a neural network is predicting to be the correct location. It is incorrectly predicting a wrong line. It is predicting this line actually. But you can see that the lines with high magnitude or confidence that the neural network is predicting is actually in the vicinity of the true fault, which is between line 5 and 6. So what we did in our learning algorithm, we created a second stage. We constructed a second graph G2, which is able to improve the accuracy by looking at its correlations between the labeled data and the unlabeled data samples. So as I mentioned, it has low label rates, so a lot of this data do not have labels. So we use a different graph and we look at the correlations between the outputs of the first stage, which is a standard neural network. We look at the correlations between different Z's, and then we use these correlations to improve our forecast. And the way we do it is very interesting. So we construct a secondary graph B for which is adjacency matrix for a graph G2. We want to incorporate both these quantities. So one is that the first stage output is more or less approximately accurate, so it is in the neighborhood. And secondly, that common events in PowerGrid generally have similar signatures. So we construct the secondary network between samples. We look at the output Z. We sparsify it so that we only have non-zero values at the neighborhoods of the predicted output, hoping that the Z is approximately accurate. We look at the similarities between Z, and then we construct a similarity matrix between samples, making sure it is sparse enough. And using this graph adjacency matrix B, we construct a different graph between samples, and then we use our neural network using this learned graph based on similarity of data with labels and data without labels to train the neural network and then learn the graph. Okay. And there is again some theoretical interpretations of what this kind of similarity-based graphs do. So in a way, it leads to directed flow of information between nodes with labels and nodes without labels in the correct order, so that you only have similar signatures leading to the design of this new labels that you construct in your training data based on similarity. But the more important result is that if you look on, we did simulations on this 120 bus system, and you look at the location accuracy rate again. In the previous case, when the location accuracy rate was going up to 50%, close to when you have label rate of 15%, now for different kinds of faults, it still goes down, but this green curve, which shows our two-stage learning framework, it is able to massively outperform all of those learning algorithms, which basically proving the intuition that operators anyways have, which is that similar signatures have similar information about similar events, and normally your approximation by just a simple brute force neural network often has approximately correct answers that you can leverage to improve our learning algorithm better. Okay. Not just that, we are also able to show that when the loads vary, that is a stochasticity in the system between training time and testing time, our proposed learning algorithm has way better performance over different kinds of faults compared to standard learning algorithms. Okay. The final part where I want to talk about is that because we saw that this power grid can have stochastic data when loads vary, we thought about can we then improve the performance for stochastic grid where voltages and injections change a lot during training itself. And one of the ways in which neural network standard in image processing domain would do is, it's a pretty standard picture that people might have seen, right? So you have a neural network which is able to do image recognition. You have a panda, it outputs a panda. You add a little bit of noise, and then all of a sudden the panda is classified as a given, right? So the way of going beyond this kind of adversarial samples is during training, you actually corrupt some of your data with noise and then train together with it so that you don't overfit the system and you are able to predict better answers in real world, right? The problem it's going to matter is they look at all kinds of data, that is data with all kinds of noise. In our particular case, what we are interested in to know is to do robustification just for power grid perturbations. Again, this falls back to the physics that I'm talking about. We just don't have any input fluctuations in the system because it's a power grid. The injection fluctuations, voltage fluctuations are all correlated in a way. They follow power flow laws and have physical constraints, right? So we want to do this training, but not for any kind of noise, but for this physical fluctuations that you can see in the system. So without going much into details, there is an algorithm called trades, which bounds this robust risk and is able to robustify neural networks to any kind of noise. What we do is basically enhance this model by fitting. So this is the data fitting normal neural network loss function. You have this addition loss function. But in our particular case, what we did is we ensured that whatever noise we're looking at follows the physical range that will be satisfied in a power grid. And not just that, we also have an addition cost function to ensure that the noise that we are looking at or the fluctuations that we are looking at would follow the physical equations or constraints that, let's say, the fluctuations between voltage and injections and so forth would satisfy in a power grid. And if you do that, what we saw is that these are all standard methods of neural network robustification. This is our physics-based method of training, where we enhance it with additional cost based on the constraints and the physical ranges. And you can see that the improvement is greater than the previous known methods. The best method with no physical training is actually quite unrobust if the noise is more, but we are able to improve it almost by a factor of 50% by using this physics-based way of learning method. And not just that, it actually leads to more efficient training as well. And the reason is that if you use physical constraints, you're able to model the uncertainty set that fluctuations can result in better than traditional black box methods of robustification. And that leads to the setting that if we have our proposed method of robustification with a few iterations, it is able to improve the performance greatly compared to standard methods. Finally, we have done all this training, we have done this design of neural networks and all that. What we were interested in is also in certification. So this is some novel work which has happened the last 4 or 5 years in understanding or bounding the maximum perturbation of neural network output for perturbations in input. So for example, you have any neural network, you have a set of inputs, they can be corrupted by adversary or noise, and your output would be corrupted and hence you'd get wrong answers, right? And there's a method which was developed at DeepMind by DJ and others, which they called as interval bound propagation. So they project the input fluctuations into a box, and then they look at how this box propagates along the neural network, ensuring that it's still tractable, and then look at what is the fraction of inputs where if the fluctuations are large, the output of the neural network will satisfy or not satisfy a particular decision boundary. So if it does not satisfy the decision boundary, your neural network will give erroneous output. So this is what is known as interval bound propagation. I'm skipping through the details of this. A method which is used to robustify or certify the neural network. What we did recently in some preliminary work is enhance this model again by using physics. So we, instead of looking at just brute force, black box, epsilon ball violations or fluctuations around the input, we looked at perturbations which are physically bounded. So they have certain ranges which follow from physics and they're dependent on each other. For example, voltages, injections, and so forth to be dependent on each other, and those boxes be correlated. And then use those physics-based perturbations to propagate through the network. And again, we show that if you use this physics, it is able to improve, not by a lot, but is able to improve this interval bound propagation-based method to certify as well as train the neural network better, and then performance actually improves if the amount of noise in the system grows. All right. There are all these other kinds of work that people have been doing as well on using provable algorithms as a starting point and doing other stuff based on it. I think I'm already going above my time, so I'll just briefly have one final conclusion slide saying that I discussed a whole lot of algorithms, and my 2-point conclusion from it is that tactical algorithms are a good way of learning and developing provable guarantees on a lot of estimation problems in power grid. But in realistic grids, you can use it as a starting point to get a preliminary estimate. And then you should use more known physics. You have intuition, you have restrictions, so that if you design a general machine learning algorithm in power grid, you can enhance its performance and at least give some guarantees or certificates on how good it performs. this estimation and learning is good, but we need to complete the loop, which is what we're doing at Los Alamos under multiple projects, is that once you've done this estimation with some uncertainty quantification and some guarantee on the performance of the estimate, you can then insert into a control algorithm. So you can have more or less plug and play and automatic control loops. So that every time there is a fault of some sort, you can then identify it, and then that identification can guide the design of the right control solution, so it can ensure that the grid does not fail and come back to a standard or a stable operating point. Okay, these are my collaborators in this. This work was started when both Misha Chekhov and Scott Backhouse were at Los Alamos National Lab. Wenting is my postdoc, would be becoming a sub-scientist here shortly, who did most of the work on the this neural network-based estimation, and a lot of follow-up work was done with Murthy Salabaka at Minnesota, his student Saurav, who's now at Facebook. Seun was a summer student here some years back who did some of this work on learning with end users. And recently we are doing a lot of the certification work or understanding the design of neural network work with DJ, who's at Google Brain. And all of this research has been genuinely supported by the Department of Energy under the Grid Modernization Initiative. We also had quite a lot of support in summer students from the Center for Nonlinear Studies here at Los Alamos, as well as the LDRD, or the internal funding projects that we have at Los Alamos. All right, that's my last slide. This is still overview of ANSI. That's our website, that's my email. So if you have any questions about the kind of stuff that we do, or are interested in collaborating or looking for positions, do send me an email. Thank you.
Okay. Thanks, Deka. Sorry, thanks, Deep, for the presentation. This was very interesting, covering all the aspects of these topics around how can we embed the learning in these important problems. I think we are over the 12 p.m. clock. Maybe we can have quick couple of questions. Are there any clarification questions from students? We can start from there. If okay, while we're waiting from a student to hear from a student, I have a question actually for you. Very quickly, I mean, this learning algorithm for, of course, both impedance and the topology are very interesting. I was curious if you ever got a chance to apply them to get maybe a reduced model for the distribution system, because, you know, one of the challenges we see in the distribution network is that we have sparse measurements, and if we want to apply, let's say, an optimization algorithm, we have only few nodes where we can observe something and control something. So it doesn't make sense to really go for the detailed network model, then just to get a reduced version of the model and maybe work with that. Were you able to do that, and how is the radial topology still preserved? What kind of observation have you had if you ever applied that?
Yeah, so if the underlying topology is radial to begin with, and that's a very interesting question actually, because it comes up that if you don't even have all the information, the leaves and so forth, the reduction of a radial topology will still lead to a radial topology itself. So the radial structure would be preserved. Not just that, you'd, instead of getting the values of the impedances, you'd get values of in some sense, the effective impedances of those lines if you have partial observability below the observations of the leaves. By which I mean, for a control task, applying this kind of algorithms might still be sufficient, because certain edges that you do not care about would somehow be effectively inserted or combined with some other edge. Not just that, at least for the learning algorithms with neural networks, and I didn't talk about that, we also did study. So normally, if you have looked at papers on how to do PMU placement and all that on power grids, it normally uses just observability analysis standard techniques in state estimation, right? So what we looked at is that instead of just doing that, if we combine that with algorithm guided placement, that is, instead of just looking at placing to enhance observability, if we place PME measurements at buses which can lead to maximal improvement in the performance of the neural network, it leads to significant improvement, at least for the particular task of fault localization. So two things. One is effectiveness can be computed, and secondly is using the performance of the neural network can also help guide the placement strategies that can massively improve the performance.
Awesome. So you do need the voltage measurement, which include both the magnitude and the angle for these algorithms, right? And those should be synchronous, or they could be asynchronous.
So for anything that we are computing quantities on the covariance and all that, we do need them to be synchronous. You don't need both the angle. Sometimes just the voltage is sufficient if you have loads on the side. If you have load measurements also.
Okay, great. I'll probably follow up with you, because we're looking into some of this specifically from the perspective of limited measurements and how you can apply some of these optimization algorithms without without unnecessarily modeling the whole grid, even if you have the model available, right? So I think that could be useful. But I'll pause here and let's see if there was question from students. I think I saw someone having any question. One question, and we'll let Deep go. Okay.
Yeah, I just have two things. Like first one is the how to measure this physics from features, like which kind of features you are extracting, and the second is that how the depth of this CNN has been derived.
Okay, so I'll answer the second question because it's slightly easier to answer. So in our cases, the CNNs are not that deep, all right? So it is not a deep neural network, it's just a neural network. So it is more or less 3 to 4. Now there is one conjecture, right? So if you have more of a physics within the system, so there's your features are physics driven, your training is physics guided, and you have constraints based on these physical laws that I talked about, right? By which you can lead to label enhancement and constraints on regularizers and all that. Quite often, by using all of that, you can actually bypass a way deeper neural network by focusing on, let's say, a shallow neural network, but with the right physics, it can still give better performance. In our case, the depth of the neural networks was done by cross-validation, all right, or by, you'd say, meta-learning in some sense. So we trained different neural networks of different depths, and we basically stopped at a point where the performance was something that we were okay with, and the depth was not large enough. Of course, if you keep on enhancing and going, you improve the performance, but maybe the improvement would not be significant to warrant that expansion in the depth. That's the second question. The first question is, how do you design physics? What kind of physics information that you do? So in this case, what we did was follow up on what people would normally do for fault localization, and this is use fault currents and or look at fault voltages and so forth. In our particular case, we picked the one which has the maximum spread of information geographically and has the most independent kind of signatures. So the problem is, for example, if you just use fault currents, right? Quite often, if you have measurements everywhere, it's great. You can get the best estimate out of it. But if you have few measurements in the system, the problem is the signature of the event is not even recorded. So which means you cannot detect it well. Now that can be improved if you have point on wave or even better readings than we have. But generally what we focused is, again, the ones with the most geographical spread and the most unique kind of signatures that we got. So that was kind of what we pursued. But generally for neural networks, and given I work also on optimization with neural networks and all that, there is some hit and trial associated with it. So if your intuition doesn't guide you, the only thing that you can do is plot different kinds of things, look at correlations, look at independence between different features, and then use that to make a selection of the right features to train.
Thank you, Deep. Okay, so if you have any follow-up question, I would recommend that you follow up with Dr. Deka over email. We'll have to wrap up today. Let's thank our speaker for a really interesting presentation and spending time with us. Thank you so much, Deep, for spending time with us, and have a wonderful day. And we'll, of course, follow up.
Yeah, thank you.